So my name is Adnan Khan, and I work I work with Anritsu, which is a test and measurement equipment company. We're over a 125-year-old company, so I guess we're older than most people over here, including myself. And pretty much we've been into the cellular business, Wi-Fi, Bluetooth business from the onset of Gs, before there were not even any single Gs, right? So today we're going to be talking about evolution of 5G. You know, it's basically evolved from release 15, 16, and 17, as well as what's happening with respect to the challenges that we're facing with them, right? So a little bit about the market and commercial services. So pretty much there are about 45 operators, based on the research we have seen, in about 30 different countries that have announced the deployment of 5G worldwide, right? And there are about 17 different operators who have already commercially launched 5G across the world. And as you can see, in the US, by first half of 2019, most operators, all the large 4 operators, had launched 5G service. Now, I saw nationwide 5G service, but 5G service in certain areas, right? So we had AT&T starting in December of 2018. We had Verizon around April of 2019, and then T-Mobile Sprint launched by May and June of 2019, right? So that was 5G service launch both for millimeter wave, which we call FR2, as well as for FR1, which is sub 7 gigahertz. And then what we also have is right around the April timeframe, we also had Korean operators launch 5G service on a much larger scale than in the US. So there are 3 main operators over there, pretty much SK Telecom, Korea Telecom, and LGU that launched 5G service. And then followed by Japanese companies, Docomo and SoftBank. They made an announcement for pre-commercial 5G services. However, the remaining other 2 operators are going to be launching sometime around February of 2020 next year. What else we also see is there has been launched by 5G by Australia also, by Telstra, as well as work in Europe also happening by a few companies. And then China has been playing a big important role. They were looking into different modes, standalone mode, started with standalone mode, and then jumped onto the non-standalone mode, right? So services in China also are planned to be launched next year. So all in all, the key thing over here is 5G is moving fast. On the network side, now if networks are launching these services, there got to be devices out there, right? So back in the Mobile World Congress in Barcelona, they had about 16 devices that were announced. This was around February of 2019. The recent survey that came out, there were about 90 devices that have been announced for 5G. And these are basically mobile devices, CPEs, different form factors, AR, VR. So I mean, the form factor of the devices are very much varying in the 5G side. Now jumping on to the complexity and technicality of things, right? So 5G is not an easy deployment. The 5G deployment changes. Unlike the LTE deployment, you have different combinations of deployments you can have in 5G. What you see on blue is the EPC, which is the Evolved Packet Core, which is what's being used by LTE right now, correct? And then what you see on green on top is the next generation core. That's when you have your fully virtualized core network, as well as your virtualized RAN network, right? And at the bottom, what you see are your E node Bs and the G node Bs. The G node B is the next generation of the 5G, similar to 5G E node Bs, right? And so the key thing is, how are operators going to transition their network? Are they just going to all jump onto 5G, upgrade the RAN, upgrade their core network, or are they going to kind of, space it out? So what we have seen so far is most operators are going with what we call option 3X that you see on the right side. That is basically keeping everything on the core network side as LTE. However, they want to milk the LTE deployment as much as possible. So what they're doing is they would upgrade and have the G node B supporting 5G in certain areas, and in other areas you're going to have LTE, right? So option 3X is the least cost-intensive way, basically, of upgrading from 4G to 5G, as well as being able to reap the 4G deployment you've had done since 2009, right? Now, where operators want to eventually get to is what we call option 2 over here, whereby you have a G node B talking to your 5G core, which is your next generation core, right? But what's going to happen is you will have different options at the same time, because you will not have ubiquitous coverage. You will still want to use your LTE network. What's really going to happen is operators will be supporting the stuffs like option 3X and option 2 also. So the essence of showing you this slide is that there is a lot of complexity in the different network deployment. Unlike 3G and 4G, there's only one way of deploying it. But 5G, there are at least 12 different ways of deploying 5G in different areas, right? And again, it's all very cost and depending on how the specifications are moving. So since we're talking about the specifications, this is showing you a schedule of 3GPP, which is the third generation partnership project. And what we can see is the first phase of 5G is what we call release 15. Second phase is called release 16. And the third phase, they don't call it a third phase, but it's probably release 17. So release 15 started in June of 2016. The first deployment of 5G, or commercial deployment of 5G, was in December 2018, right? So in a very, very short time, the deployment is happening even before the specifications are getting completed. So that's one of the few challenges that we as a test and measurement equipment we're facing, is to create solutions whereby the standards have not been completely defined. And how do we do that? We do that by partnering with different chipset vendors, making common assumptions, and contributing to the specifications body, right? So what you can see for release 15 is they had an early drop, main drop, and then there's a late drop also. Initially, there was only one drop. But when things don't move as you expect them to move, then you can stagger them out. As you can see, the early drop was on option 3, which I talked about. It froze in around June of 2019. And around September, they had the main drop, which was talking about a standalone mode. In a standalone mode, there is no LTE anchor. You have all 5G core as well as you have 5G G Node Bs. And then you have the late drop that happened September of this year. And that was kind of focusing more on option 5, option 4, option 7, which are the other options, which are not as important right now. But that being said, phase 1 was up to completion. Thankfully, it has been completed. But phase 2 started also around June of this year. So there's a lot of content happening in release 16. But the release 15 part, what it's focusing mainly on is throughput. We don't care how efficient that throughput is, but it's throughput, throughput, and throughput, right? So you want to hit 20 gigabit per second. You want to hit 10 gigabit per second on the uplink, low latency, high reliability, but it's primarily focused on the throughput portion. So moving on, but we're not really paying any attention right now to the efficiency, to the battery life. So we are just pushing the devices to get high throughput, but the optimization is a big part of it. You know, especially when you're deploying millimeter wave, it's very important to understand what is going to be the interference between the sites, because the inter-site cell distance is going to be very short. It could be somewhere like 100 to 200 meters, right? So what happens as we move on from release 16 to release 17? Release 16 introduces a lot new features. The big feature in release 16 is how do we optimize all the work that we did in release 15, right? So you have a device that's going to be supporting different radio access technologies. How are you able to make sure that the power consumption is as good as LTE, if not better, right? So those are some of the challenges that you got to face. In addition to that, they have discussion on talking about V2X. Release 15 also has V2X, which is your autonomous vehicles, but it's more of a platooning kind of application. It's more of an application whereby you have sensors and you're sending message to the device. But release 16 is going to introduce what we call side link on NR. So NR means new radio, how device can communicate together without going to the network, but using the NR bands. Because the NR bands are a lot different, the structure is a lot different than it is for LTE. I'm not going to go into the details of all of them, but another very, very important portion of release 16 has got the unlicensed band. So if you all are familiar with what was in LTE, we had LTEU, we have LAA, we had enhanced LAA. There are different ways of optimizing and using supplemental bandwidth. You know, frequency spectrums are really, really expensive. People spend all the way to $8-9 billion on spectrum. So nobody can say no to unlicensed spectrum. So unlicensed spectrum is going to be a big, big part of 5G. If you look at it, FCC has recently talked about licensing between 5.9 to 7.125 gigahertz of unlicensed band. If you go from 54 to 71 gigahertz, 64 to 71 gigahertz, there is about 17 gigahertz of unlicensed band available to be used. So we're going to tap into that, but that's all coming in release 16 and release 17. Now what release 17 is introducing is looking at frequencies higher than 52.6. Release 15, release 16 was focusing on frequency of 50, and that's pretty high. I mean, we've been using frequency 6 gigahertz and below, and all of a sudden we jump from 6 to 28 or 39 gigahertz for commercial deployment on your devices, it was unheard of, right? But now we're going to go into a new territory, and it comes with new challenges. You have new propagation challenges. The physics cannot change over there. And then there are other items like industrial IoT and R 4.0 and whatnot, right? So a lot of work is happening. Release 15 is just the tip of the iceberg. That's the takeaway from it. But there's a lot of underlying features that are going to be part of Release 16 and Release 17. So this is basically a drop of how the frequency ranges are structured in case of 3GPP. We have what we call FR1 that goes from 410 megahertz all the way up to 7.125 gigahertz. It was 6 gigahertz before, but then they talk about spectrum that goes from 5.9 to 7.125, and then so the range of FR1 from sub 6 became sub 7 gigahertz. And then we had FR2 that goes from 24.25 to 52.6 gigahertz. And anything between FR1 and FR2, since FR1 and FR2 already coined, we'll call it FR1.5, right? So that's the way it is. But the key thing to note over here is if you look at the band structure on the second column over here, the 3.3 to 4.2, or I would say to up to 5 gigahertz band is a common band. It's a harmonization band. That's the kind of band that's being used across the world. I mean, you have areas that will use millimeter wave. You will have areas that will use the low bands like the 850 megahertz or so. But the 3.3 to 4.2 gigahertz band is an important band. That's also being listed as for auctioning. It's probably called Auction 105 by FCC. That's going to be listing the 3.7 to 4.2 gigahertz band. So we talk about the different frequency ranges. Another very, very important part of what's happening in Release 15, how things are changing, is what we called dynamic spectrum sharing. So that is a new feature. It is part of 3GPP Release 15. But what this feature does, it allows operators to be able to deploy and activate 5G services on FR1, on LTE bands, without waiting to have the spectrum carved out. So if you have to go through the whole bureaucratic process of getting the licensing, carving out spectrum, it could take years and years. But this specific feature, dynamic spectrum sharing, does enable operators to launch 5G as well as launch 4G on the same spectrum. So you can use something like, say, band N5, and that could be used for 5G. It could be used for 4G in the same location. That is a key aspect of it. That's how the initial launches because most of the bands in the US primarily are FDD bands. And when we started 5G, it was on TDD. We had the Sprint N41, and we had all the millimeter wave bands. But now we're getting into the FDD-centric bands like N5, N71, N66. So that's going to be a very, very important player over here. So moving on, what are the other challenges that we see, right? So this is a pictorial view of a device. In Release 15, a device can have many arrays, many antenna panels on it, right? But for initial release, you will only have one antenna active at a time. And that was simple. And the reason why they did it was just to make the testing part simple, right? But there are other complexities, right? You have one device that's going to support FR1. It's going to support FR2 as well. It will support LTE, it will support 3G, it will support Wi-Fi, Bluetooth, GPS. It has to support all those different radio access technologies, right? So testing does become very, very complex. In addition to that, when you're in looking at high frequency millimeter wave, you have those array of antenna panels, could be a 2x8 array, and they have to go through a process called beamforming on the device side. Beamforming is so you can basically focus your energy in a certain direction. And there are different ways of doing beamforming. You can have digital beamforming, you can have analog beamforming, you can have hybrid beamforming, right? But they all have the pros and cons. But the intention of telling you all this is the device is very, very complex. And basically it has to support multiple bandwidth, multiple subcarrier spacing, multiple radio access technologies all jumble into a device. So it does certainly get very, very complex and expensive. So if you're doing something like a digital beamforming, that's going to drain a lot of battery life because you're going to have separate transceivers connected to each of these RF chains over here. So that's something to factor in. And one of the most important part from a millimeter wave perspective is not being able to test in a conducted fashion. Historically, all the LTE testing that was done, not the OTA part, now all the FR2 testing has to be done OTA, over the air. Because one of the key thing is obviously your antenna could be part of your RFIC, so you cannot physically connect to it. And even if you could connect to it, then the loss would be so high that you would not be able to get correct measurements. So this is pretty much, I've outlined it over here, is initially when we're testing a 4G device. So a 4G device, you have a baseband, you have your RFICs that will have your low noise amplifiers, your PAs and whatnot, and then you have your antenna. So you can do your conducted testing and you can test this portion and this portion separately because you can have a disconnect between this part, right? But when you come to 5G millimeter wave, there is no disconnect. It's just an integrated part. So it's very difficult to tell if the issue you're having is with the transceiver or if the issue is due to the antenna. So that introduces more complex challenges. In addition to that, the other challenges that we have in 5G, especially testing millimeter wave, are the test times, right? There are tests that can take up to a day to run, just one single test. What happens in case of 5G in millimeter wave specifically is you have different grids. You have a spherical grid around a device. And it depends how many points you want to take those measurements and how many polarization, vertical or horizontal polarization that you want to connect. That way you can find out what the device RF characteristics are, in 360 degrees. So as I said, a test can take, a day. A minimum, a test would take at least an hour and a half to 2 hours to run for millimeter wave. So Anritsu has been investing into finding ways on how we can lower the test times. There are different ways of doing it. There are different algorithms that we can talk about offline. But that's one of the key challenges are the test time, because the longer the test times, the longer it takes for the device to market, to launch, right? And obviously the expense of it. The other items that we want to talk about is the specifications, the complexity of the specifications. What you can see on this column here is only 3 specifications that were to be tested for an LTE device. Now when you have this is from a conformance specification. And when you have a 5G device, you have up to 7 different specifications only for 5G. And then you have to test the specifications for 4G also. So the test times does become long. And the other issue is the specifications have not been completed. So it's a lot of times it's like the blind leading the blind. But you make assumptions, as I said, and that's why you're able to complete. A lot of these launches have happened without the specifications even getting completed. So that's another big challenge that we face from a device test perspective. Now we talked about the device, but a lot of stuff is also happening on the network side, right? So if you look at the network side, there are, as we move on into release deployment, as I said, release 15, what we're seeing right now, just tip of the icebergs. You have a lot more verticals for low latency, mobile edge computing. What we do in mobile edge computing is, in a 5G core, we separate the user plane and the control plane. And we try to move the user plane as close as possible to the end user. So you could have different gateways that are deployed close to where you want to provide your service. And you can have your control plane centralized in one area. And that helps in the mobile edge computing, as well as it helps with the high reliability and low latency communications, right? We want to make sure the device can change the states as quickly as possible and be able to. Now the latency portion it's very tricky. Latency is not just the latency of when you send the device, sends a message, it goes to your G node B, but you have to look at the overall latency. You have to look at latency in your RAN, you have to look at your latency in your core network, and also in your edge network. And you got to look at them separately, right? But what you try to do is you try to bring your edge network as close as possible to your user, whereby you have low latency applications. So we have solutions that we look at both from a device test perspective as well as network test perspective. And some of the solutions are basically looking at the user equipment and kind of mapping it out. We talked about the RAN network, the core network, and the edge network. So for the edge network, you would want to measure the round trip latency. And then you'd also want to measure the latency in the RAN network, right? And then you have the concept of network slicing, whereby you are dedicating resources for a certain sort of applications. That's a very, very important piece that was not there in 4G. It gives it's very powerful because it gives the operators the capability to choose, basically charge users based on the application they're running, one. And number two, it gives the flexibility to operators to be able to load balance the core network they have. If a certain resource is being used for public safety, then they can reduce it and they can use that resource for another sort of, maybe for mobile broadband or for some sort of a low latency application. So again, we play a very important role into the end-to-end network testing piece of it, right? So key thing to note over here is, in case of 5G, is the device test is certainly an important part. There is a big chunk of stuff happening on the network piece also. But as I said, that the network piece is going to take longer for it to hit the point whereby you have a true 5G core everywhere, right? Currently, a lot of operators are still using the 4G core. Once the core becomes fully virtualized, then you have the concept of network slicing that comes into play. So in summary, what I would like to say is we participated in the different areas of testing. It could be RF front-end testing, component testing at the initial side, or chipset level integration. The chipset goes into the device. The device, basically you test with the real network. So we play a role into the different aspect of testing, from certification, conformance, as well as mass production testing. But all those testing that happens, it's very, very challenging because of the fact, as I said, the specs are not completely done. We're still learning about them, and there are new applications coming up which is going to open doors to different sort of scenarios that we have to do. So it's very important that we are able to keep up with the specifications, work very, very closely with the OEMs and the chipset vendors. So last but not the least, thank you for your time.